Hi, I'll be talking about Rubik's cubes and pretty much the whole maths behind them, mainly in the areas of combinatorics and group theory. As a first question, I want to kind of find out how many pieces are how the Rubik's cube is made up, so that we can further analyze it and pretty much apply a method that can be applied to most puzzles, so to speak. Puzzles, I mean, all different kinds of Rubik's cubes, including 2x2s and n by n cubes, to find out how many ways we can shuffle them. That's our end goal. So we want to find out how many ways we can shuffle a said Rubik's cube. But as for starters, we're gonna find out how many ways we can assemble this cube. So if we had to take apart one, we would get 8 corner pieces, which have 3 colors on each small side, so to speak. We'd have 12 edge pieces, and we'd have 6 center pieces. This is what a dismantled Rubik's cube would look like, sort of. So we're going to be putting each of these pieces back together in the proper formation. Well, how can we do so? So if we had to construct the Rubik's cube just using the corner pieces for now, we'd have 8 of them. We'd have 8 slots, and inserting them one by one, we'd be reducing the number of slots by 1, and we'd get a total of 8 factorial ways in which we can arrange these pieces. Similarly, for the edge pieces, we'll get 12 slots, and each of them can be arranged in 12 factorial ways. So if we multiply 8 factorial and 2 factorial, we get all the ways in which we can slot in, so to speak, all of the pieces. But we have a small peculiarity in the pieces, sort of. Each piece can be inserted in more than one way. They can be oriented. I'm going to use the word oriented, as opposed to permutations, which are what we used earlier for slot arrangements. Each edge piece can be inserted in one of 2 ways, which are distinct, and that happens by permuting the colors, just cycling through the faces of the small cube. And for corner pieces, we have 3 ways of orienting or rotating, so to say, each cubelet in the same spot. So the total number of ways would be this very large number, which is 519 quintillion, if I'm not mistaken, by considering the permutations and the orientations of each small cube, of each small cubelet. However, this number, this 519 quintillion, includes certain cube configurations which are not valid. We can't not solve. By not valid, I mean not solvable. So just taking apart and reconstructing a Rubik's cube might end up in something which we might not be able to solve, because we can't get there with the original moves. So we have, we can rotate the cube in a certain way. We can't just twist a corner on its own. We can't just swap 2 pieces. We need to abide by the order which the moves are applied. So the real number of how many ways can we shuffle a Rubik's cube is actually smaller than this, and we'll figure it out. There are 3 restrictions, so to speak, on the placement of each piece. So suppose we are rebuilding a Rubik's cube, but in the correct formation. So each piece is in the correct slot, and all of the faces have different colors completely. The 3 restrictions go as follows. So the last edge piece must be oriented correctly. What do I mean by that? I mean that when you get to the last edge piece, so you finished, you've rebuilt your cube, and you go to the last piece, you want that piece, of course, intuitively to be the correct, slotted correctly. I mean, to have a complete cube, the last one must for sure be correct. As demonstrated in this picture, this is an example of a wrong edge orientation, where this specific state, cube state, is not solvable by traditional means, so to say. The second restriction is a wrong corner orientation, which is twisted. We would say we would twist a corner, which might happen on some cubes as you solve it. And obviously at the end you'll figure it out. You figure out that you can't really move on forward from the state. So when you get to the last corner piece, we need to make sure that it is slotted in, there aren't three possibilities, but there is only one last possibility to orient the last corner piece. The last restriction goes as follows. We cannot swap any two corners. So when we get to slotting in the corners, so we're not talking about the orientation, but their permutation rather, we cannot just choose any place for the last two pieces. And why is that? That's because in the cube, we have something called parity, and we must maintain an even parity. What do I mean by parity? I mean that whenever we swap two pieces, whenever on the cube, it is apparent through some move that we swapped two pieces, they could be edge or corner pieces, there will be for sure another two pieces that are swapped. So a total of four pieces that would be swapped within themselves. So we can't have just two by themselves. And this is an example that portrays the swapping of the front top left and front top right corner pieces swapped, but oriented correctly because we have the white on top. So this is the product that we had earlier. And if we eliminate from the first line, if we eliminate the incorrect orientation of the last corner, the wrong orientations of the corner pieces, we would change that 3 into a 1. If we wanted to eliminate the incorrect orientation of the last edge piece, we would turn the last 2 of that product into a 1. And we would also eliminate the incorrect, all of the incorrect at the end of the day, place swappings or placements of the last two corner pieces. So if we recall the expression that we got earlier, 8 factorial times 12 factorial times 2 to the 12 times 3 to the 8th, and divided by 12, we would get 43 quintillion, which is the real number, so to say, of the real number of ways that we can actually validly reconstruct a Rubik's Cube. So this is kind of half of my talk regarding combinatorics and why we have such a large number of distinct configurations. This is this number of distinct ways in which we can arrange a Rubik's Cube through traditional moves, so to speak. Now I'm going to talk a bit about groups, and well, as most of you know, to talk about groups we need to introduce notation. So this is a transparent cube, and I'm going to refer to each side by the direction it's facing, more specifically with the first letter of the direction it's facing. So we have front and back, left and right, up and down. These are, well, moves that are applied to the Rubik's Cube, and they're denoted by the first letter, as I've said. And it's very important to note that one move is defined as a clockwise quarter turn. So clockwise, as if you have to perform it clockwise, as if you're facing the face you're turning. So for the front face, that's quite trivial. But for the back face, you would have to sort of turn the cube around, look at the back face as if it was in front, and rotate it a quarter turn clockwise. These are the 6 moves we can do on a Rubik's Cube, the 6 operations. And we have sort of the formal definition of a group. So what really is a group? A group is an abstract algebraic structure which is made up of 4 rules. So whenever we have, a system, be it whatever, and we observe these 4 axioms, which I'll explain shortly, we can say that this system is indeed a group. A group, in its essence, is a set and an operation, any arbitrary operation, which we can apply to any 2 elements, a binary operation which we can apply to 2 elements of said group, of said set. Sorry. So the first axiom is closure, and that just means that for every 2 elements that you picked within the set, if you perform the operation on them, you'd get another element in the same set. So we're never getting something which is not a valid, in the context of the Rubik's Cube, that is, we're not getting something which is invalid by doing any 2 moves. A clear example would be the natural numbers under addition. For any 2 natural numbers, if you add any 2 natural numbers, you'll get another natural number. I mean, it follows. That's closure. Associativity is, the arrangement of the brackets, so to say. More specifically, the order in which you perform the operation does not matter, kind of. So we could do A and B first. We could do A star B first, and then star C. Whatever the star may be. It could be a plus, it could be a minus, it could be a +2. From the abstract point of view, we kind of detach ourselves from any restrictions to tie us down, sort of. We have the existence of the identity. So in this set, there must be there must exist an element which, when applied to any other, when we perform the operation between the identity and any other element, we get back the first element. So in the integers, it would be, if we consider the integers over addition, +0 would give you whatever number you gave it first. So 3 + 0 is just 3, and therefore 0 is our identity element. In the case of times, we'd have 1 as the identity element. So it really depends on your set and on the operation. The last axiom is the existence of the inverse element. So briefly, it's the ability to get the identity element back from any element in the original set. So a simple example would be the integers. You pick any positive number, you're guaranteed to have, the negative counterpart, and when you sum them up, you'll get 0. So if you have 4, you're guaranteed in the system, in your set, to have a -4, and 4 plus -4 is 0. And that's the identity that we started with in the third axiom. If we can sort of prove the presence of these 4 rules, so to speak, in our system, then we can conclude that our system is indeed a group. Now, to be able to define, to be able to prove, what I want to do is I want to prove to you that the Rubik's Cube forms a group, or rather, all of the configurations in which it can be shuffled. To do that, I will need to go into a bit more detail. So our set is not a set of Rubik's Cubes. We recall that a set is just a collection of items, objects, and these objects can be, any abstract concept that we may choose. Over here, I have 3 examples: ULR, U, and LR. These are all valid elements of our set, which are in turn moves. We'll call our elements of our set G moves. So ULR is the quarter clockwise turn of the upper face, followed by the left face, followed by the right face. We have another move with just one single rotation, and we're basically going to include all of these. But we have a small restriction, because some moves will result in the same configuration, and we know that in sets we cannot have duplicate entries, sort of. Although they may not appear duplicate, we will say that we can equate two elements of our set if and only if they result in the same configuration. So that's what I say in this point. So that's our set, and the size we found the size of the set. It's around 41 quintillion. It's the combinatoric part of the talk. The operation is very simple. It's almost like a function composition, almost, which for any two moves, m1 and m2, if you perform the operation m1, if you perform the operation between m1 and m2, the result will be just a move where you first do m1, whatever it is, be it an upper turn or a front turn, and followed by m2. So we need to kind of follow the order. An example is here. We have L, R, B, U, and D, F, L, and the composition of them, we will just append the second move to the first one, and we get a new move. That's our operation. So proving it. So what I want to show is that given these definitions, that our system is actually a group and a valid one. So to prove closure, it's quite simple. Well, we already defined it that way. So if our operation creates a third move from any given first two moves, it follows sort of that the third move must be in the set, or at least we know we have something equivalent to it. Associativity also quite intuitively follows, because, well, if you take the cube and perform any two moves separately, so I don't know, m1 and m2, if you perform those first, by consequence you'll be performing m1 first and then m2, because of how we define our operation, and then m3. But really and truly, that's just equal to doing m1 on its own, and then m2 composed with m3, which is just m2 first and m3 first. So if we had to try this out on a Rubik's cube, we'll end up with an identical state at the end. The inference is a bit trickier, because to prove the general case, it's not so straightforward. So here I'm going to show the simplest case, which is just one quarter turn. And to reverse a quarter turn in the clockwise direction, you would say that we could rotate it in the reverse clockwise direction. You would be right, but we are restricting our moves to only clockwise rotations at the moment. And therefore, to reverse a single clockwise rotation, we need to perform another three in addition to that rotation. So in case anyone doesn't believe me, this is what happens when you apply one left clockwise quarter turn to a solved cube, and followed by what happens when you rotate the same side for another 3 times. For simplicity, I guess, to be able to explain it a bit clearly, we're going to denote the inverse of any arbitrary move as m to the power of -1 to kind of mimic the notation of multiplication. You know, m times m to the -1 is just 1. And we'll define L prime to be a reverse clockwise quarter turn. So all these are just really equivalent, only that they're shorter to write down, and we're able to construct a bit more elaborate moves using this notation. To reverse any arbitrary move, basically, it is not we need not only to reverse it, but we need to also invert it. So we need to reverse the order in which the moves, any number of moves were made, and invert them one by one. So kind of like the transpose of a matrix, AB all transpose is B transpose A transpose. So this is kind of an example of it, I guess, where we would turn around all of the terms. We would switch the places of the first and last, etc. A rendition of this is the 6-spot algorithm. It's called so because it generates 6 distinct spots on the Rubik's Cube, sort of, but in reality it just moves all of the pieces. And we show that when we perform that algorithm, that move, and then the reverse of it, will effectively get the original state, which can be anything. You can start from anywhere and you'll end up at the beginning, but for visualizing it, we always start from a soft cube, because that's the most easiest. It's the easiest to figure out. The last axiom we need to prove is the identity, and this is just the move of doing nothing. I guess you could turn a side through 0 degrees about any axis, and we say that the group has a right identity. We can multiply any move. We can apply the operation star. Let me not use the word multiply to any move, and if you do any move and do nothing after it, you'll just get the move on its own. An interesting small proposition that we may propose is the existence of not multiple but an infinite number of distinct moves that leaves the cube untouched. And what I mean by that is there exists an infinite number of moves we can generate, which are not in our set, of course, because we defined it to be so that it doesn't contain duplicates. They're basically, we can basically make up an infinite number of identities, and I won't prove that. Maybe someone will come up with that. I've proved the 4 axioms, and we can now conclude that the Rubik's Cube, or rather a group of Rubik's Cubes, is actually, yes, it is indeed a group, and that it follows the 4 axioms. I could talk about much more, but my time is up. These are just some of the things that are behind the maths of Rubik's Cubes, and what we can sort of extrapolate from all the concepts, abstract concepts behind it. Thank you for listening.